So let's first talk about current. So we're going to do one by one. Okay, so what is current? Current is the rate of flow of charge. Okay, so what is rate of flow of charge? That means how fast the current is flowing. So from here, there are three separate formulas that we're going to learn. The first one is this, which is current is N times Q over T. So in this case, your N here refers to number of electrons. Q here refers to the charge of each electron, for example, and T will be the time taken. But of course, you can actually use any type of charge. For example, if you're talking about proton, then this will be a charge of proton, this will be number of protons. Or maybe it could be alpha particles. That means this will be number of alpha particles, and this Q will be the charge of each alpha particle, which is 2 times E. So this formula actually comes from here. You know why? Because Q here represents total charge. And total charge is equivalent to number of particles carrying the charge times the charge of each particle. We multiply, you get total charge flowing. So when do we use this formula? Is when they want to find number of charged particles flowing or number of charged particles flowing per unit time. Then we take current divided by Q. Alright? To get number of particles per unit time, or you just want number, there is not current divided by charge times time. Okay, so this is the first one. So the second one is when we talk about this, and what will happen is you can find the total charge that flows, total charge that flows. So how do you find the total charge that flows? You can take current times the time. But this is provided your current is constant. But your current is not constant, the total charge that flows, you must draw the IT graph first and its area under the IT graph. Okay, so you must do that. Okay. So as we were mentioning just now in the introduction, right? So voltage is actually energy per unit charge. So it's energy per unit charge. So energy per unit charge, there are three types of voltages: potential, PD, and EMF. Potential is at a point. PD and EMF is a difference in potential between 2 points. When the potential drops, the difference is called PD. When the potential increases, the difference is called EMF. Okay, for example, let's say you have a cell here. Okay, so they didn't draw the cell here, so I add the cell here. Okay, let's say there's a cell here. And we connect 3 voltmeters, one across your cell, one across this 20 ohm resistor, another one across this 10 ohm resistor. Right? So what you will get is your voltmeter will show you 12 volts, 8 volts, and 4 volts. So what does it show you actually, the voltmeter? The voltmeter actually shows you difference in voltage. Why? Because your voltmeter has 2 terminals, right now, and you need to connect both terminals in order for your voltmeter to show you a reading. So for example, if I give it values, let's say the potential at this point here is 0 volts. So that is called potential. Why? Because it's a single point. But the voltmeter shows me there's a difference of 12 volts between here and here. So it means on the other side, the potential therefore must be 12 volts. So that is also called potential. So the difference between these 2 points is called your EMF, because from 0 to 12 the difference is 12, and because the potential increases, so we call it the EMF. Now throughout this line then, because when the current flows through this wire, we will assume that the wire has no resistance, so there's no loss in energy here. So if there's no loss in energy here, so throughout this whole thing is still 12 volts, so here it is still 12 volts. This is called potential, is still 12 volts. But then the voltmeter shows you the potential drops by 8 volts. Because the difference between these 2 points is 8 volts. So if the potential is 12, the 8 volts here is actually PD because it drops. Because when the current flows through a resistor, it loses energy, loses electrical energy. Because the electrons will collide with the atoms of the resistor and will lose the electrical energy as heat. So therefore the potential will drop. Drop by how much? 8 volts. So because it drops by 8 volts, this difference in potential is called PD. And therefore the potential here, once it drops by 8, will be 4 volts. So this is called potential. So but you remember here, why is it called EMF? Because when the current passes through a cell, your chemical energy is converted into electrical energy and transferred to your electron here. So therefore we will consider this as potential increasing, so the difference is called EMF. But when the potential decrease means the electrons are losing electrical energy. So when it passes through this side, because there's no resistance, there'll be no loss in potential, so this side is also 4 volts. But then it passes through this resistor where the electrons will collide with the atoms again, so it will lose energy. So it loses energy, so the potential will drop by 4. So 4 volts potential drop by 4, so your balance potential will be 0 volts. And 0 volts will be the same throughout here because there's no loss in energy here. So always remember, when potential increases, the difference is called EMF. When potential decreases from 12 to 4 or 4 to 0, then the difference is called PD. So what is actually the definition of EMF and PD? So you will notice, as what we mentioned earlier, the EMF of the cell here, which is 12, will be equal to sum of PD. Because whatever energy the electrons gain in the cell will be lost completely before it comes back to the same point. Alright, so this will form the basis of Kirchhoff's second law in our next chapter, DC circuits. So the definition of PD and EMF are pretty similar. It comes from the same basic formula, which is W over Q, W divided by Q, where V is either PD or EMF, okay, but W is energy change. But what kind of energy change? That's where the difference is. If you want to define PD, then it is energy converted from electrical to other forms of energy, right? For example, heat, light, and all that, per unit charge. And for EMF, the W here represents the energy converted from other forms of energy into electrical energy per unit charge. So basically they have the same formula. W here is energy change, also energy change. But this W is electrical to other forms of energy. This is other forms of energy to electrical energy, but per unit charge. So the formula will tell you that the units can also be written as joule per coulomb. So joule per coulomb can also be said as volts. So you can either call it volts or joule per coulomb. It's just another unit for it. So that's a definition. Now, another illustration of what the definition means. For example, remember in our cell, right? Okay, just now remember the voltmeter showed you 12 volts. So that means for every 1 coulomb of charge, so assuming there is a flow of positive charge 1 coulomb, when it passes through the cell, every coulomb will gain 12 joules of energy, electrical energy. But when it passes through this resistor, where the voltmeter showed you 8 volts across it, so this is 12 volts across, is 8 volts across, so it means that for every 1 coulomb, it will lose 8 joules. And remember the last one, we said that the voltage was 4 volts, so therefore for every 1 coulomb of charge, it will lose 4 joules of energy. So that's what it means by voltage. So the formula for potential, we don't learn in AS, we learn in A2. But potential, how we find is just by like how I taught you. So if you start from 0 volts, increase to 12, so the potential is 12. Then it drop by 8 volts and the potential is 4. Then it drop by 4 volts, the potential is 0. So that's all what you need to know about potential. Okay?